Hello everyone, my name is Jeffrey Gillen and I'm a researcher at the University of Arizona. So today I'm going to talk to you about rangeland monitoring with high resolution imagery. This has been my primary research topic for about 9 years or so I thought it was about time I came out with a summary of my thoughts. In this presentation I will cover the past, I'll talk about where we came from and how we got to the present, I will discuss the state of the art, and then finish with steps we need to take to more thoroughly integrate drone imagery into rangeland management. This presentation was originally given at the Society for Range Management Conference in Denver in February of 2020. So let's start with typical field monitoring. By using transects or vegetation frames, we can get really detailed information, such as vegetation composition. But the limitation is that these methods are very expensive and slow to do over large geographic areas. It is only practical to visit a few key areas or random plots. As a consequence, a lot of range management decisions are based on small data. Additionally, there are some indicators we cannot measure very well or maybe not even at all from the ground. So how do we overcome the geographic limitations of field methods? Well, we can turn to remote sensing. Satellite imagery, of course, can cover enormous areas such as regions or even whole continents. However, the drawback is that the data is often too coarse to identify range indicators of interest, such as species composition. Recently, there's been an effort to take field data and model it to satellite imagery such as Landsat. So this upscaling approach can then predict range indicators across satellite coverage. These tools are truly amazing, yet they can't do everything. There are some indicators that will not work well with this upscaling approach. Also, the results are modeled results, and so they're not really observations. So it seems there is room for some high-resolution imagery to complement these upscaled products and also complement field data. So let's now look back over the last about 20 years or so and talk about some of the notable milestones that brought us to where we are now with drone imagery. To me, it really all started in the late 1990s, with the beginning of all digital workflows. So we started collecting aerial imagery with digital cameras, which made computer analysis much more streamlined. Then in 2001, that was the year of the first paper I could find that used drones for some rangeland application. In 2001, Quilter and Anderson from BYU demonstrated how we could estimate browse from an RC plane. A few years later, also at BYU, Perry Hardin and collaborators showed us how we can map invasive plants, also from imagery from a fixed-wing RC plane. About that same time, Terry Booth and his collaborators at ARS, they were collecting very high-resolution imagery from an ultralight plane, and they showed us the power of image interpretation. So you can look at this high-resolution imagery and identify a lot of features on it. It's a great complement to field data. And I got to mention the work of Albert Rango and Andrea Laliberte down at the Jornada Experimental Range, which is a unit of ARS. So they produced a pretty substantial body of work showing how we could use drone-based imagery for rangelands assessments, inventories, and monitoring. I arrived at the Jornada to work in 2011, so I was there kind of at the tail end of it. But it struck me as pretty groundbreaking stuff. But the thing that I noticed is that it was very large, a big footprint. It required a lot of personnel, a lot of certifications, and a lot of expensive equipment. So in a way, Since 2011, I've been trying to carry the torch of this research, but do so with a smaller footprint, do so a little cheaper, a little bit more efficiently, and hopefully that could become more practical for adoption by more people. So along those lines, there was a great paper that came out in 2010 from Dan Doyce and Ellis. This demonstrated a computer vision technique called structure from motion, multi-view stereo. And they did it to demonstrate they could three-dimensionally model vegetation. And they did it from a kite, which would then soon become drones. So this paper was interesting because it showed us that we could use consumer-grade cameras to still make very high-quality image products. In that same year, Parrot released the AR drone, which was the world's first consumer drone. So it was off the shelf, ready to buy, ready to fly. A couple years later, DJI, the Chinese company, came out with the Phantom 1, and that really marked the the explosion or the uptake of people getting into drones. It became suddenly much more easier to do when you didn't have to put together the aircraft. In 2013, Anderson and Gaston believed that small drones would revolutionize spatial ecology. I think they were right. Drones give us this low-cost access to an interesting stream of data. That's it's at a scale somewhere in between field data and satellite imagery. It gives us this interesting perspective we didn't really have before. In the most recent 5 years or so, I call peak drone. So there's been massive adoption in geosciences, in forestry, in range, etc. And that brings us up to the present day. So I've been focused on using small, low-cost drones for range monitoring for several years now. So why small drones? Let's just go through the list of reasons why. Why these are transformational tools. First, we can create very high-resolution imagery capable of measuring many indicators. We'll talk about that here in a little bit. In fact, we can measure some characteristics of soil and vegetation better than we probably can in the field. We can cover large areas with it, larger than we can with the field methods. It can be relatively inexpensive. It's highly portable. Some of these I can put in a backpack, hike out to a monitoring plot and deploy it there. And it's on demand. As long as the weather is cooperating, we can go out and fly and collect data. So from these low-cost drones, we are primarily creating 3 different imagery products to measure the indicators. The first is we are creating orthomosaics, which are basically 2-dimensional maps. We can make digital elevation models and other associated products with that, such as canopy height models. And then structure from motion point clouds. So point clouds can be really realistic 3-dimensional renderings of the landscape from which we can measure things. So here, this point cloud is a photogrammetry point cloud. We can also do the same thing with LiDAR. So drone-based range indicators. Over the last 20 years, there's been significant research on demonstrating which indicators we can reliably estimate from high-resolution imagery. They include vegetation cover and composition, with some caveats, of course. We can estimate canopy gaps, vegetation heights and structure, forage production and biomass, forage utilization, and even soil erosion. So now let's go through each of these with a bit more detail. So vegetation cover and composition. This is probably the most sought after information for range managers. what type and how much vegetation is out there. Accordingly, cover and composition has probably been the most researched topic, with high resolution imagery. Typically, we would do this with two-dimensional orthomosaics, and typically we would do some kind of thematic classification. For example, here I'm classifying this image into grass, mesquite, and bare ground, into pretty simple classes. And that's where drone imagery really does well with these general classes, such as plant functional groups or life forms. It becomes much more challenging when trying to distinguish grass or forb species. Some species it's going to be possible, but not like what we can do in the field. Drone imagery methods can cover large areas, but we cannot get detailed species composition like we can with field methods. Canopy gaps. So we can measure the size of bare patches, how many there are, and how they are connected really well from drone imagery. This can be useful for assessing the impact of wind and water erosional forces. All right, so let's get to the indicators where drones and photogrammetry really shine, and that is the 3D indicators. We can make hyper-realistic models of the landscape to estimate heights and structure better than we probably could from the ground. We can also estimate biomass and forage production, from these 3D models, and we can also estimate forage utilization. So what you're seeing here in red is forage that was consumed by cattle. We did a project on this a few years ago. Then finally, soil erosion. So with drones and photogrammetry, we can survey topography and its change extremely well, with centimeter precision. If we do it over time, we can quantify and visualize the movement of soil. We can see where erosion is occurring, and we can see where soil is being deposited. So applications. Of course, there are many applications where drone data can be used. Here's just a small list. I'm sure there are more. For example, we can map invasive species. We can use imagery for restoration projects. We can use them for assessing wildlife habitat quality. We can even use drone imagery as a tool for rotational grazing. There's just a lot out there we can do with drone imagery. So with 20 plus years of work on this topic, we know that high resolution imagery can be used for range monitoring now. But where do we go from here? In my opinion, we need to work to organize the body of knowledge a bit more on this topic. So we need to professionalize drone imagery methods. And there's already a template we can follow, and that is essentially what we have done with field methods. So this image here is the cover of the monitoring manual produced by the Jornada Experimental Range. The idea behind the manual is to get everyone on the same page regarding methodologies. It has simple descriptions and illustrations, in its an attempt to standardize data collection methods so data is comparable across time and space. I don't think drone imagery methods can become as standardized as field methods because I think the drone methods are just more complex, but I do think we can move in this direction a little bit. So I think there are basically three things we need to do to professionalize drone imagery products, drone imagery methods. The first is to do more studies where we compare imagery indicator values with traditional field methods. And we're going to have to do this in multiple geographic areas. Second, we need to make the whole endeavor of drone imagery more cost-effective. And third, we need to work on reproducibility. So this is about documenting our workflows, sharing them with each other, and then seeing if we can move towards best practices. Okay, so let's go through each of these three steps in a bit more detail. So the first step is to continue doing studies where we compare imagery and field indicator results. As an example, I did a study in the Northern California BLM district, which is outside of Susanville, California. On the map, you can see several blue dots. These are range monitoring plots. In fact, they are actually BLM AIM plots, which stands for Assessment, Inventory, and Monitoring. It is the BLM's national scale data collection program. So I embedded with a field monitoring crew and went out to each of these plots. The crew did their field measurements, and I flew drones and collected a lot of imagery, and then we did a massive comparison between the results. This is what an AIM plot looks like. It has a spoke design with 3 25-meter transects. Along the transects, the crew does a suite of measurements including line point intercept, vegetation heights, canopy gaps. They also do a species inventory and do interpreting indicators of rangeland health. I can't measure all of these things from drone imagery, but I can do several of them. So my objective was to develop a workflow to estimate 3 indicators. I estimated fractional cover, canopy gaps, and also vegetation heights. So I'm going to show you just one result from this study. Cheatgrass is an invasive species in this part of the world. It's become kind of a problem. So what you're seeing here is a scatter plot for fractional cover of annual grasses. The horizontal axis shows fractional cover estimated from drone imagery. The vertical axis is the estimate from field measurements. So you can see we have a fairly robust linear relationship between the two methods, but it's not perfect, and that's okay. Imagery methods are not going to perfectly replicate how we measure things in the field. What is more important is identifying what the relationships between the methods is. Are there systematic differences? If we're going to integrate imagery products into monitoring programs, we need to know how they will relate to the legacy field data. Perhaps we can develop a correction factor between them. For this study, I also learned about the importance of timing or season of data collection. The imagery was collected in late June, which turned out to be a little too late to capture green cheatgrass. So the grass was senesced and harder to identify. With drone imagery monitoring, we're going to have to think about what the best times of the year are to identify features of interest. And these comparative studies are going to have to occur in multiple places around the country and probably the world. Different ecosystems and different vegetation communities are going to have different method relationships and different seasons. So the second step toward professionalizing drone imagery methods is to make the whole endeavor of collecting, processing, and analyzing imagery more cost-effective. So most research has been one-off demonstrations over relatively small areas. For small projects, our methods are fairly cost-effective right now, and we should be doing that right now. However, in the future, as we rely more on drone imagery as a source of information and try to integrate them with national programs such as AIM or NRI, we're going to need to scale the production of imagery. We need the ability to efficiently produce large amounts of data. So over the last year or so, myself and my colleagues in Arizona have been working on this problem. We have discovered that we can basically connect a series of existing technologies together to greatly increase the speed and the scale of drone imagery. So here's what we have found. First, we need to be collecting imagery with drones that use real-time kinematic GPS, or RTK. So this is all about pinpointing the coordinates of the camera in the sky for every photo it takes. If we have centimeter precision, we can do something called direct georeferencing. And this allows us to eliminate ground control targets from our workflow. This is an enormous time and cost savings measure. So with RTK, we can create high quality products over hundreds of hectares. Without RTK, we are kind of stuck with a few plots and maybe a few hectares of coverage. So along with data collection, in the near future, one pilot should be operating multiple drones at the same time. We have not pursued this yet because legally I need a special waiver from the FAA to do it, but the capability exists now. I can connect 2 or 3 drones together now and fly in formation to cover a lot of land really efficiently. So once we have terabytes of raw imagery, we need to process them efficiently somehow. But if you've ever done structure from motion, you know that generating large point clouds can be very computationally heavy. But we figured out that we can, through high performance computing, or HPC, we can make multiple instances of the photogrammetry software and have them all work in parallel. So for example, we had 15 instances of Agisoft Metashape working together. So a high image project that might take a week on one desktop computer can now be finished in about 5 hours on the HPC. And it's just a miracle to behold once it gets rolling. So in tandem with HPC, we are scripting all of the image processing steps. Because we are using RTK drones and eliminating ground control, we can fully automate the photogrammetry workflow with Python scripts. Okay, and now that we have large data sets of high quality image products, how do we efficiently analyze them and get the indicators we want? So large imagery data sets can quickly overwhelm desktop software such as ArcGIS. So we need to move towards a cloud computing model. The most mature platform out there right now is probably Google Earth Engine. So we uploaded all of our orthomosaics to Earth Engine. It leverages large computing power to quickly analyze big data sets. We are able to execute machine learning classifications and other algorithms to estimate several indicators. Additionally, Earth Engine can easily be shared with colleagues. The scripts can. It's easy to generate summary reports and also embed the maps and the reports into websites. So I think more development needs to take place for cloud computing to become easy and powerful for range monitoring, but Earth Engine is a good first step. So the third and final thing we need to do to really professionalize drone imagery is to work on reproducibility. Now this is all about documenting our workflows, sharing them with the community, and working towards best practices. For example, there are many decisions we need to make in the whole drone imagery workflow, the whole cradle to the grave. There's just many things we have to decide to do. For example, what vegetation community are we working in? What's the best season of data collection? What kind of aircraft are we using? What kind of sensor? Are we doing radiometric calibration? What's the resolution of our imagery? Or what kind of spatial referencing are we doing? Are we doing RTK? Are we using ground control points? Are we filtering our point clouds? And if so, how? What's our analysis format? So there's just a lot of decisions we have to make. As you can see, this is just a subset of everything we have to do. So for the study in Northern California, here is our choices. This is our workflow decisions. In a different study in Arizona, these are the options I chose. So if we can document and share the fine details of our workflows, can we correlate workflows with good results? Can we curate best practices for any given indicator in any given vegetation community? That's the goal here. So we also need to be documenting the image processing pipelines. How exactly are we going from raw drone imagery to indicator values such as vegetation heights? There's a lot of steps you can take in that processing flow. And the best way to document this nowadays is through scripting languages such as R or Python. So how do we document and share these workflows? Where on the web do we do that? There are some interesting protocol repositories out there right now. One is called Protocols.io. Another is called Protocols Exchange. These are interesting because you can document an image workflow and then get a DOI or a digital object identifier with it. That makes it searchable and citable. That's great, but to me, these repositories seem a bit too broad in scope. Perhaps we need a Rangeland drone website itself. Now, I've been kicking around this idea for a while. The website should have workflow descriptions from published and unpublished projects. It should have downloadable scripts to help other practitioners automate image processing. I have several that I would like to give out to people. But also it should have contextual information about why we're doing things. So this should include short wiki articles on methods and theory. It could have webinars and other trainings. And then there should be user forums where other drone users can just chat with each other about what they're doing. Okay, so concluding thoughts. It has been really interesting watching this field develop over the last 9 years. Drone imagery has gone from expensive and impractical to cheap, easy, and practical for use right now. In my opinion, drone imagery will certainly be a standard tool for range monitoring, but it will be interesting to see how it unfolds. A small word of caution though, drone imagery is unlikely to replace most of the monitoring we're doing now. Maybe in a few cases. It certainly won't replace most of the methods and programs such as AIM or NRI. Imagery cannot replace a field ecologist that can read the land. Imagery from any scale has a difficulty doing that. Instead, drone imagery will enhance and complement field data and satellite imagery. It has the ability to cover much larger areas than field data while retaining very high resolution imagery. It does a fantastic job for 3D indicators and opens the door for indicators not measurable from the ground, such as landscape metrics. So thanks for watching. Here's my contact information if you'd like to reach out for collaboration or advice on your own drone projects. Thanks.